Good morning, my name is Mohammed Moise. Today we'll be doing a 316 project on transfer learning for low resource language understanding. In this project, we basically tackle a real problem that affects us in the UAE, how to make AI understand the way we actually speak in the mix with English, using code switching. Um, so, okay, let's move on. So what is the problem over here? Now, there is a linguistic inequality of AI. Now, how can we adapt an English LLM to understand languages that lack large-scale training data? Now, the thing is that um, uh, there's a linguistic inequality. Most large language models like ChatGPT are trained like primarily on English. They work great on English, but when they're mixed of language in the UAE, it doesn't really understand. And the thing is that it's far more of a unique problem because in the UAE we have a unique situation. Gulf Arabic is our daily language, but we mix, uh, but, uh, but we mix it constantly with English. On social media, you'll see posts like "MashaAllah, khidma kanat amazing." Okay, which means the service is amazing, good God willing. If you give this to an English-only model, it understands amazing but misses the Arabic context. If you give this to a modern standard Arabic model, it may understand al-khidma, mashallah, but it will miss the English intensifier, amazing. So you don't really get a complete context. And the thing is that, especially when each or one of these things is missing, it's kind of hard to give an accurate sentiment analysis on this. So our task is to basically have both of them incorporated. Sentiment analysis and code switching text, which basically helps determine whether it's positive, negative, or neutral. Okay, so why are we using transfer learning? So now if you use a random model, train it from scratch, it would require a lot of data sets, weeks of training, a lot of time it takes. With transfer learning, you have a pre-trained model, you fine-tune it to your needs and requirements over here. Need of 1,500 examples, very decent. It doesn't require a huge data set, doesn't require a lot of time implications. It's very resourceful to our needs and requirements here, which is far more necessary and far more convenient. Okay, moving on. So what is our data set over here? Now let me talk about our data set. We created a synthetic database of like 1,500 code switched examples. Now, why synthetic? Because there's no publicly available dataset for labeled Gulf Arabic code switch text. The Twitter API now costs money, and existing datasets are modern standard Arabic and not dialect as you find in a Khaliji Arabic. So we created a synthetic one, and we are doing this to emulate real datasets. So now you can see there are 600 positive ones, 600 negative ones, and 300 neutral in our dataset. So why do we have this sort of inequality over here? So we're trying to emulate real datasets. In real datasets, you will tend to find like positives 40% and negative 40%. As I've tried looking up in like Twitter's in MSA datasets as well, you'll find 20% to be neutral. So we're trying to emulate real datasets. So training on real datasets, we're trying to emulate that. Now let's run down with a few examples. Now you have mashallah, خدمة كانت amazing, that's a positive one. Now أكل شيء جدا يعني it's not worth it. Negative. Both of them combined. عادي المكان was okay. عادي in Arabic means it's alright. المكان, like the property was right. Oh, so what is our approach right over here? We compared two transfer learning approaches. First, a full fine-tuning. This updates all 60 million parameters of the model. It gives the model maximum flexibility to adapt to a task, but it's very resource intensive. Second is LoRa, which stands for low rank adaptation. It updates only 0.56% of the parameters. It is 34,064 trainable parameters compared to 60 million over here. This is very, very less. Now, we also implemented both frameworks as required. PyTorch with Hugging Face for both approaches, and TensorFlow with Keras for full fine-tuning version. Now, coming to model configuration, we use a flat T5 small as our base model, 80 million parameters, small enough to train. Essentially, it's 80 million parameters, small enough to train like on Google Colab for free. For full fine tuning, we used a learning rate of this. And yeah, but for LoRa, we use this for each of them respectively. We basically trained everything on Google Colab on the Tesla T4 GPU. Full fine tuning took like 230 seconds, and LoRa took around 174. It's quite far more efficient having to do it on local GPU. And what are our results? Okay. Full fine tuning achieved 98.67 accuracy. LoRa achieved a 90.67 accuracy. The key difference is about 8%. But at the parameters, but when we look at the parameters, full fine tuning takes 60 million parameters, and LoRa takes 344,000, which is basically 99.4% fewer parameters compared to full fine tuning. Training time, LoRa was 24% faster because it achieves 92% accuracy with like 0.5, less than 1% of its parameters. This is a huge efficiency gain if you're deploying it on a phone or a small device. LoRa is the way to go, and if you have like a powerful server and need maximum accuracy, go with full fine tuning. That works well. Okay. Now we have our confusion matrices. The confusion matrices show exactly where each model made its own mistakes. So for full fine tuning, you can see correctly classified 195 out of essentially 200 negative examples. 196 out of 200 examples, but only 20 out of 25 neutral. So neutral is where it struggled. For LoRa, you can see a similar pattern, but more mistakes. 180 negative correct, 180 positive correct, and only 12 negative correct. Now, what does this tell us? Both models are excellent at distinguishing positive and negative, but you can see quite a elicitable new problem over here, that it's very difficult in identifying neutral correct. Now, why is that so? Because our data set, neutral was only 20% of our data set. The model didn't see enough of neutral examples to learn them. This is a classic data imbalance, but the thing is that we're trying to emulate real data sets, which do tend to have 20% neutral data. So yes, that is the reason. Now, cultural evaluation. Now, how do we do this? How do we ensure that this could be implemented? So accuracy alone doesn't tell if a model actually understands Khaliji Arabic. So we created our own metric, dialect authenticity score, DAS. DAS measures out of all correctly classified examples how many maintain authentic Gulf Arabic markers like religious expression like mashallah, dialectical words like shakhbarak, common phrases like haram. If a model gets a high accuracy but low DAS, it means that it's guessing based on English words. A high DAS means it's actually learning a culture. Our results in fine-tuning achieved 98.7 DAS, nearly all correct. LoRa achieved 91.3. Both models have a good cultural authenticity, but full fine-tuning did it quite better. This proves that transfer learning doesn't transfer vocabulary, it can transfer cultural understanding too. Now we can go to like failure analysis. No model is really perfect. Now, first, neutral examples. Remember, 20% of our data. Now, first for neutral examples, it was very hard to identify them. Remember, neutral is only 20% of the data, and model didn't learn this as well, this class well. This is a data problem. If we had more neutral examples, performance would improve, but because we're emulating real data sets which tend to have 20% in terms of its split comparatively to other classes, it is usually 20%, so that is why it is like this. Second is mixed negation. So for example, like ma good, in Arabic, ma means no. So ma good means not good. But sometimes the model saw good and ignored ma, classifying it as positive. This is a linguistic challenge, negation that is crossing language boundaries. This is very context related and something that requires a bit far more variables in terms of uh, in needs of context of both the languages involved. Third is sarcasm. AI is not good at basically retrieving good sarcasm. These failures tell us what to work in the future. What are our key findings? Now we transferred successfully vocabulary in both languages. The model learned words like amazing, mumtaz, mumtaz, uh, equally code switching patterns. It understood mixing languages doesn't change the sentiment, and cultural context proven by our high DAS scores better ensures a better implication rate. Now, what was the challenging part? Neutral examples, cross language negation, and sarcasm. So if you're choosing an option for maximum accuracy, full fine tuning wins. For parameter efficiency, LoRa wins by a massive margin because it relies on less data sets. And for deployment on limited resources, LoRa wins. For cultural understanding, full fine tuning wins. There's no single winner, but it really depends on what you need. Which comes up to our conclusion over here. Summary of what we have here. We successfully